And we're back. Welcome back and happy Thursday. Today is the last day of classes. The subject of today is the final project, a simple file system. Before we begin, some administrative bits. The reading, it's not a lot, pages 529 to 554, rounds out our last subject and one of the more humble yet very important subjects, namely file systems. So this is the final day. Congratulations. I know things have not been normal, very different due to COVID. Everyone working from home or online, can't see each other in person regularly, but one day it will return back to a semblance of normal. Important thing is to stay healthy, stay safe. Want to see you back, the seniors who are graduating. Congratulations to those who are not seniors. We'll see each other in person in the fall of 2021 and perhaps even spring of 2021, depending on how things go with vaccines and such. But nonetheless, what is left? Final exam period is Thursday, 10th of December, 10:30 a.m. to 12:30 p.m., so it's a week from today, during which you'll be giving your project presentation. The last day of finals is when the final projects are due, and that will be the 11th of December at 8 p.m. Please make sure you're staying on top of the due date. It's electronically via Blackboard. So, the file system. The file system is involved in a lot of things. If you think about it, it's fairly humble. It might seem somewhat mundane, but the file system is literally everywhere. Let's say you're streaming video via YouTube, or you're recording, mastering, editing, and rendering a movie. Well, you make heavy use of your file system. Those video files are pretty big, especially as the resolution increases, and those files, those video files, you slice them, you splice them, you do all sorts of things, insert effects and animations, and all of that places pretty big demands on your file system, and many video editing programs make specialized use of your file system in order to make them efficient. Let's look at something like Google Street View. Lots and lots of 3D high definition panoramic images of streets and locations all throughout the country, and different countries for that matter. You type in an address, you pull up the Google Street View, and you drive down the street in a virtual sense, advancing, click, click, click. Well, certainly, where do you think those images are stored? In a data center, somewhere, perhaps a storage area network, on ultimately a file system. So we see the file system, while it's not the star of the show, as it were, for Google Street View, it is essential to both the performance of this application as well as the look and feel, because you don't get Street View images without files that can be transmitted across the internet in a relatively efficient manner, such that when you click, it's seamless to you. Well, there's also a walking version of something like Street View. This is for Apple Maps, and it's a walking map. If you've ever gone to a city where this map has been recorded, it's like a GPS for walking around. You have stores, you have directions, how to get to the subway, and so forth. And so people walk around with these backpacks. They're recording video, panoramic, as well as depth information, and they're creating walking maps. Now, where do you think all of those walking maps are stored? Well, certainly you can beam them across the internet, but when you're recording them, it's fairly high-density data, and this high-density data is stored somewhere in this backpack on you guessed it, a file system. So here we have the file system is underneath the covers, making this thing work, and it has to accommodate real-time streaming data. So this file system is different from the file system for Google Street View. This is also different from the file system for your video editing software. This particular file system has to be well tuned to storing real-time streaming data. So yet again, our file system is behind the scenes doing its job. Now, when you look at different web services, you have Google Cloud Platform, IBM Cloud, Microsoft Azure, Amazon Web Services, and there are many others. Now, of course, one of the key elements of using cloud services, you're renting capacity on demand. Now, if you're renting this, you have to meter it, that is, measure the amount of compute capability that you're using. And guess where that accounting stuff goes when it's calculated? It goes into, you guessed it, a file system. So underneath the covers, file system, while it might seem like the more mundane, not the star of the show, it's sitting in the background reliably doing its thing, underlying yet another important application. So let's look at a basic web server for like an e-commerce site like Amazon. Now, of course, your request comes in, and when you go shopping online, you're clicking, guess where those products come from? They come from a catalog, from a database, and that database is backed by a file system. Now, certainly the database might have access to the raw file to have very finely or highly tuned use of the file system, but nonetheless, without this file system, you wouldn't efficiently present these items to make it easy for you to search and retrieve things that are relevant to a particular product need. And then let's look at cloud storage. It's very popular these days. iCloud, Dropbox, I'm a heavy user of, OneDrive, Google Drive, all sorts of cloud storage media platforms. And there are many new up-and-coming cloud storage platforms that are tuned to particular types of data, like a picture file cloud storage facility. Now, of course, the second word in cloud storage is storage. And without a file system, that cloud storage isn't going to work very well. Take something, for example, like Dropbox. It's one that synchronizes between different installations of file systems. So it's a replicating file system. Without a specialized and the quote-unquote right file system in place, Dropbox is not going to work very well. It has to compare differences to what's on the server, to what's on the local installation, and then send across all those updates necessary to keep them all consistent with one another. And so here we have all these amazing applications that people use heavily today. And underlying it is this seemingly humble, nondescript part of your operating system. But if we look at it, the file system is really, really the hero of the show, unassuming nonetheless. So the file system doesn't get top billing. It's not the one that people really pay attention to. Its presence is absolutely everywhere. Now, in a lot of cases, when you think about all the exciting things in operating systems, file system doesn't execute programs. It has nothing to do with processes, but without the file system, you wouldn't be able to store that program's image on disk, and you also wouldn't be able to traffic in its executable format, which is kept in chunks on the backing store. So a file system, while it's not a process, it's key to processes. Now, the file system isn't involved in the running of a process. It doesn't schedule or dispatch, but it holds parts of processes and data that can't fit in memory, namely your pages. So your file system is not involved in the dispatch action, but it's heavily involved in the underlying facilities and resources you need in order for scheduling and dispatching to really work. And so, the file system, this is not entirely true. It does schedule things. It schedules disk transactions. It needs the cylinder, track, and sector for some transaction, the size of that particular item you're going to read or write, and the destination, where it's going to go, what block of memory is going to source that data, or what block of memory is going to sync that data. And so, yes, it does schedule. So it does process-like things in that it's scheduling. And we saw that depending on how you schedule, seek, look, see, look, first come, first serve, scan, see, scan, we can get different performance given the same disk with the same physical parameters for performance. And a file system certainly is not virtual memory. It doesn't present the illusion of contiguous memory. But as we saw with page replacement, the file system is key to the operation of virtual memory. And so it doesn't execute processes, doesn't schedule processes. It has nothing to do directly, at least, with memory, virtual memory. But without that file system behind the scenes doing its job, you don't get any of these other things. And so while it might seem like the file system isn't a major part of your operating system, it is absolutely a major player, and dare I say, the most important player, because without the file system, none of these other things will work very well. Now, of course, the problem and the reason why the file system doesn't get top billing, everyone's always excited about process scheduling and process stuff and virtual memory and what happens with non-uniform memory access and all that wonderful stuff. It doesn't get the same treatment. But a good file system, and the reason for that not getting the top billing, is that a good file system is hardly noticeable. And if you think about it, if the file system does its job well, you just assume your system works and you don't care. But you only notice that the file system is there if something goes wrong or if the particular choices in place for the file system are insufficient for the task that you're trying to accomplish. Okay, so let's take a look then at the final project more specifically. Your mission is to implement a non-hierarchical direct access file system. Now, of course, it's non-hierarchical, so that means we're not going to have two levels of hierarchy. We're not going to have directories or indices on disk, but nonetheless, it's a direct access file system. Now, obviously, we could take a whole semester to implement an entire file system with directories and links and arbitrary graphs and things like that, but we're going to focus on some key aspects of the file system, not the entire thing. We're going to focus specifically on block management. And that is the accounting in place or management for blocks, meaning their allocation and their deallocation. Now, as we saw with main memory, the allocation of a frame to some page is the goal of memory management. With our file system, the goal is the management of blocks of disk. Now, we're going to simplify this, and we're going to have a single raw file as the disk. But if you were doing this for real, you'd be managing the sectors, tracks, and platters associated with the disk device and the DMA transfers for the I/O transactions as well. But we're going to simplify this because we're only going to do this in a week for the final project, synthesizing material that we've covered all semester, and in particular with an emphasis on the last two modules, mass storage and file system interface. So recall when we talked about a file, what is a file? A file is nothing more than a one-dimensional array, a sequence of blocks. Now, these blocks happen to be stored on disk. And so the same way you'd think about an array as being a data structure, we call a file system a set of so-called on-disk data structures. And so essentially what the file system is doing, it's managing on-disk data structures. So the fundamental unit of storage for these on-disk data structures is a single block. And so a file system manages these blocks, and a file is considered as a sequence, one-dimensional array of these blocks. And so each file is some collection or some subsequence of this contiguous sequence of blocks laid out as an on-disk data structure. And so let's take a look at the specific file system that we have for the final project. We start out with a free block list, and that free block list is an accounting system that manages your blocks, and it does so by noting which of the blocks on disk are free and which have been allocated. Because if you're going to read and write information to and from the blocks on disk, these on-disk data structures, you have to know which ones are free, they're not taken, you can use them, store data, and which ones are occupied, which have data. You can't store anything if it has data, if it's already been allocated. So this free block list is used to manage which blocks are occupied and which blocks are unoccupied or free. Okay, so let's take a look at the blocks. We have a set of data blocks, and each block is 512 bytes. A byte is 8 bits. And this data block section of your file system is just a set of chunks, and these chunks are 512 bytes long each. So this is where the actual file data is going to go. Now, of course, when you allocate a block to a file, if you only use 1 byte out of this 512, you're going to get internal fragmentation. So these blocks are not fractional. You allocate blocks to files, whether you only need 1 byte within that block or all 512 bytes within that block. And so this is this part of the on-disk data structure where the actual file data exists. So you have an array on disk of blocks, and each of these blocks is a standard size, 512 bytes long. So this array of blocks, each block within it is identified uniquely. So we have a block number, and in this case, we have block number 0, and it's 0 space. Block number 1, we have a total of 8 many blocks numbered 0 through 7. So a block number describes the particular block or offset for that block within this on-disk data structure or array of blocks. And so this free block list maintains a one-to-one mapping of each block. So if we have, as depicted here in the figure, if we have 8 blocks, we're going to have a free block list that has 8 entries in it. So this free block list is also an array, but this particular array is an array of bits. So here, this position is the 0th offset bit within this free block list, and here is the 7th, so we have a total, in this case, of 8 bits. So the free block list is an array of bits, and each position in that array represents the allocation or unallocated status with the corresponding data block. And so we mark in a position in this free block list a 0 if the corresponding block is free, and a 1 if it has been allocated. And so in this particular case, we have block number 2 has been allocated. You'll notice here, offset 2, 0, 1, 2 in the free block list, it's marked as 1. And we've colored in block 2, data block, meaning it's been filled with some data. It's been allocated. But all the other blocks, 0, 1, 3, 4, 5, 6, 7, are free. They have not been allocated. And so in this particular case, if the free block list had 8 positions and we had a total of 8 blocks, if we were to allocate block number 2, we would mark position 2 within the free block list, that bit, the second bit starting from 0, it would mark that as a 1. Okay. So this is how you allocate, and therefore when you deallocate, you're going to strike that out as 0. And when it's 0, it signals to the file system that that corresponding block is available to be allocated to a file. All right. So what does it mean then to write a file? If you're going to write a file, well, the first thing you have to know, a bunch of questions you should ask yourself, how much data are you writing? Because if we're writing 1,000 bytes of data, you're going to need 2 blocks. If you're writing 100 bytes of data, you're going to need 1 block. So the first thing you need to know is how much data are you writing? Okay, check. From that, you know the block size, and you can calculate how many blocks you need. So, of course, you're going to use the ceiling function because you can't write a fractional block. You have to allocate a whole block, even though you might only need 2 bytes of it. So you calculate how many blocks you might need. So there's another question. So then the next thing you're going to do after you've answered these two questions, you set aside the blocks that you need in order to write that file. So let's say if you needed 2 blocks, well, you allocate a block. Well, we know that block 2 is already taken, so we might allocate block 0. That gets a 1, and block 1, that gets a 1. So now we've reserved blocks 0 and 1 by writing a 1 in the free block list for those positions. And now we write the data to those blocks once we've allocated them. Okay, so this last position here, this section of the file system, it's an array of inodes. And this is how we represent a file in the final project. So what is an inode? It's a Unixism, and it's not a real inode. There's some aspects of it. An actual inode in Unix is a linked list, so you're going to have a next inode pointer, but it mimics it to a degree, given the scope of the time we have for this project in the semester. And so you have an array of inodes, and each one has a standard format, and each inode is going to represent a file. So in this particular case, we have 4 inodes. That means this file system can have 4 files. And so let's take a look from the specification of the final project for the inode format. So an inode has the following format. We start out with 64 bytes as the name field. We have 4 bytes for an integer field, and that integer is 4 bytes long, and that's going to be the size of the file. It's how many bytes that you have in the file. Now, it just so happens when you create the name of the file, we're going to use ASCII text to represent that name. And then that last field of the inode, a single inode, is going to be 32 integers for a total of 128 bytes. It's 128 bytes because 32 times 4 bytes per integer is equal to 128 bytes. And so each one of these 128 integers is going to be a number starting from 0, and that number that you store in each one of these integers, these 32 integers, is going to be the number associated with the data block. And so if I were to write a 1 here, it means that data block 1 is part of this file's data. If I were to write a 2 here, that means data block 2 is part of this file's data. And so you can treat these as pointers, and they actually are pointers because they're data structures that store a value, and the value is a reference to some other piece of on-disk data structure. And so we have here 32 integers where each integer is a so-called block pointer. So let's take a look at the name field. That's the file name, and it's limited to 64 characters because it's 1 byte per character, and we'll assume it's an US English ASCII character, not a localized representation because it uses more than 1 character per entry. And so you have the name field, and the name is going to be limited to 64 characters, and it should be unique for each file. That means that extensions have no meaning. So while you call it hello.txt, that .txt, the extension, means nothing in this file system. We're just looking for a sequence of characters. And the name should be unique for each file. Now, of course, let's assume that capitalization is not respected here. So hello, with a capital H, .txt is going to be the same as hello with all lowercase .txt. So it should be unique for each file name, and extensions have no meaning. Okay, so let's look at the size field. Well, the number of bytes the file contains is stored in the integer, with 4 bytes long, in this size field. An integer is 4 bytes long, so therefore this size field, the number of bytes stored in this file, named by the name field, is going to be stored in this next position on disk data structure inside of the inode. And then lastly, the block pointers are an array of integers, and these describe the block numbers containing the file's contents. And so the file's contents for the file, let's say for a file I had 3 blocks, the first block pointer is going to be the first 512 bytes. The next block pointer is going to be the next 512 bytes. And then the next block pointer is going to be the next 512 bytes for the file. And so when you think about a file and you write it, you allocate your blocks from the free block list, and then you populate those blocks that have been allocated with the contents of the file. All right, so that's the block pointer section of the inode, and all of this together corresponds to a single inode. So if you look at how big an inode is, it's a data structure. You have an array of inodes on disk. The first 64 bytes is the name field, the next 4 bytes is the size field, and the last 128 bytes are the set of 32 block pointers. All right, so let's take a look briefly at the code provided. And with the live session, I'll certainly go into NetBeans and go over some of the code, but I will not do that for the public YouTube. If there is a professor out there who wants to use this material, please contact me at my email, and I will gladly share the solutions as well as the code with you with the right attribution, as well as making sure that you actually are a faculty member and not a student looking for a solution. But nonetheless, let's take a look at the code. And so there are a bunch of Java files. It's all in Java, and it uses a raw file to simplify things. And we have disk.java. The goal of the methods in disk.java is to set up the on-disk data structures for the file system. So it'll format our disk to have the free block list, the inode list, and the data block list. And so disk.java sets up the on-disk data structures for the file system. It provides for the reading and writing of the on-disk data structures, namely the free block list, the inode list, and the block list. Free block list.java has methods for the allocation and deallocation of free blocks. Inode.java has a bunch of accessors and mutators, so it's a kind of wrapper class. And this is for setting and getting the file name, setting and getting the size, setting and getting the block pointer. And so inode.java are those methods for interacting with the various fields within the inode data structure in its in-memory representation programmatically. Main.java is a driver program. It starts the whole file system. So it instantiates an instance of a file system with the underlying raw file. It also serves as a test harness for writing, deleting, and reading files. Filesystem of .java is the only file that you're going to be modifying in your implementation for this assignment, for this final project. And so filesystem.java handles the opening, closing, creating, deleting, reading, and writing of a file. Now, your focus on filesystem.java is limited only to block allocation. So you're going to focus on the write method and the all throw IO exception, the allocate blocks for file method, and you're going to give it the starting inode and the number of bytes, and the deallocate blocks for file method, you're going to give it the file name and an integer starting inode. And so you're not going to change the signatures. And in the comments, you'll see code that says you will implement the following. So please make sure to implement the following and do not modify any other part of this assignment except for these 3 methods. And the comments are there. So you will not be changing the test harness driver. You will not be changing anything. Everything else there works, and it was carefully designed for the purpose of this assignment. So that's going to be your focus. So let's look at what your task is. Well, you're going to design the algorithm for writing. You're going to design the algorithm for block allocation, design the algorithm for block deallocation. Let's look at some do's and don'ts. It's fairly straightforward. Now, you notice I said design algorithm. And so when I say design algorithm, I mean actually spend the time designing algorithm. What are things you should do? Study the code. Don't just jump in. Understand what the code is doing in all parts before you enterprise to design your algorithm. One good way to do this is to bring it up in the debugger. Start with the main routine in the main Java class and step through it and just familiarize yourself with how the thing works. Think before you implement. It's much easier if you thought about things carefully. Exercise algorithmic thinking for this one. When you implement things, implement incrementally along the way and test what you're doing. Don't just write a big ball of code and then try to get it to work. That's a recipe for failure. If you're going to iterate over something, write the empty loop first and print out some things along the way. Convince yourself incrementally as you do things that they work as you anticipated. Take the time, and this is probably the most important one, take the time to design and write out your algorithm. So you look at a data structure or data structures, you look at a sequence of steps, and these sequences of steps are going to operate on these data structures. So think about the data structures, the steps, and what these steps are performing on the data structures, because you need to know what the data structures are before you perform the action and what those data structures are after you perform the action. So it's really, really important to take the time to design. Do not just jump in and start hacking away. So an example of this, let's say you said step one, read free block list from disk, bring it into memory. Loop over the block list. B is equal to the current block. If B is free, allocate it. And then append it to a list of allocated blocks. And then return the allocated blocks. Wow, that looks like an algorithm for something you do to allocate blocks before you're going to write the file contents to them. And so take the time to do this step. This is a lot more straightforward than it appears, but you have to invest the time to think and to design and write out your algorithms. Do not hack your way through a solution to the problem. It is a recipe for failure to jump right in and try to solve it all at once. Think about the different pieces, think about the data structures, the steps, and how those steps operate on the data structures. Don't modify parts of the program that you're not supposed to. So don't go implementing and changing things outside of Filesystem.java. Everything else is off limits except for those 3 routines that I mentioned earlier in Filesystem.java. Don't submit something that doesn't compile and run. My policy, if it doesn't compile and run, 0 without consideration. I won't even look at it to grade, just a 0. Do not forget to submit everything needed to run your program. That means you don't just submit Filesystem.java. You submit a complete program that compiles and runs, and make sure you submit it. If you are using NetBeans only, you can submit your code inside of the IDE file. That's only if it's NetBeans. Otherwise, submit to me all of the Java files needed to run your program. Do not submit the raw disk file. I don't need that. It creates the disk file. Don't submit individual Java files. Put it in a zip file, zip only. I don't want to see 6, 10 Java files attached to the Blackboard submission. Don't forget to test what you submit. So if you create a zip file, when you do, make sure you unzip it and guarantee that what you got out of that zip file can actually compile and run. Don't forget to submit your presentations separately. I'm going to underline that. There are 2 separate submissions, one for the presentation and the other for the project, which is the code and your write-up of the project. Your write-up should include your algorithms. Don't forget the due date and time. Please mark that down now. Put it in your smartphone, set reminders daily, what have you, whatever you need to do. And don't wait until the last minute. Waiting until the last minute, 5 minutes before it's due to submit it, is no excuse for not getting it in. Make sure you budget your time. All right. So lastly, this is the end of everything we've done this semester. And you are to congratulate yourself on a job well done. We've done a lot of things and gone over a lot of parts of the operating systems fairly comprehensively. And so let's just give and have a moment of applause for you and all of the stars of this show throughout this semester. We've had OS definition. Operating system structures. Processes and inter-process communication. None other than threads and multi-core threading. The one, the only, scheduling and multi-process. Who can forget synchronization? And with the assist, there's main memory. Always on the call, virtual memory. Underlying a lot of things, your mass storage system. And last but not least, that beast from the east, it's your file system interface underlying it all. So you are to congratulate yourself. We've done a lot rigorously and covered every main aspect of operating systems. Things have not been normal. You've slogged through it. I appreciate that. Hang in there. Just 1 week left. I look forward to seeing your implementations. And please do not hesitate to reach out to me. I'll be on Slack the entire time throughout the week. I look forward to your implementations. Remember to think, have fun with it, and you also learn something. So with that, please stay on top of the key dates. And as I always end each class, things are getting rough out there COVID-wise. Please stay healthy, stay safe, and I will see you around hopefully in the spring. Take care.